Okay, so I'm taking the same situation and we're looking at the concentration graphs now for adding ammonia and for removing ammonia. Now, although at equilibrium the concentration of the reactants will remain constant, they are not the same. They are not equal. You get me? Because the mole ratio is 2 moles to 1 mole to 3 moles. These moles, and concentration is moles per volume. You will not have the reactants or the reagents as present as equal concentrations. So here we go with concentration. So we've got a concentration of ammonia, a concentration of nitrogen, and a concentration of hydrogen. We could also have a moles of ammonia, a moles of nitrogen, a mole of hydrogen, or we could use volume. But I'm choosing to use concentration now. So this is concentration, and it's measured in mole per cubic decimeter. I'm going to leave that out now over time. So your ammonia is the only reactant. To reach equilibrium, the concentration of ammonia will decrease until it reaches equilibrium. Then the concentration of the ammonia will stay constant. Maybe I should drop it a little faster. Then, at the start, there is no nitrogen. So this is the concentration of ammonia. That is how the concentration of ammonia changes over time until it reaches equilibrium. The concentration of nitrogen will do what? It will increase. So I'm going to do it in a different color, and it will increase like that. Why am I putting the nitrogen's graph lower than the ammonia's graph? The mole ratio is 2 to 1. Okay? So this, your mole ratio is 2 to 1. So this is not a rate graph. So there will be a lower concentration nitrogen in the reaction mixture because the mole ratio is 2 to 1.
Oh, okay. That's the reason for this.
Yes. Okay. I'm just working with a logic number. The situation can change once they give you specific values. Okay. But the concentration, so that one is the concentration of the nitrogen graph. What will happen to the concentration of the hydrogen? It will also gradually increase, but if we look at the mole ratio, what will it do? Is that making sense? Is it making sense? Okay. So here, new equilibrium is established. At that point, we've got equilibrium.
Is the green one hydrogen?
Yes, sorry, let me do that one.
So is red the equilibrium?
Red is the place in time where equilibrium is reached.
So, ma'am,
Yes.
the equilibrium actually be there by, like, where they intersect? Because it doesn't make sense if, but then, like, it doesn't make sense if the green is on top of the blue, you know?
Why not? Ratio is 2 to 3.
So So how are
Look
you?
at the balanced equation. Ratio
Yeah,
is 2 to 3.
Yes, ma'am, I get that. But then, shouldn't their point of intersection then be the equilibrium?
Mm-mm.
Why is it so, ma'am?
Because they haven't reached equilibrium here yet. This is not a rate graph. It's the way the concentration, the amount of the reactant is changing. So you started off with no hydrogen, but actually, if I look at that, the concentration of hydrogen that forms is 3 times more than the concentration of nitrogen that forms. This is not a scale graph. I'm just introducing the way to think here. Okay. Wait. So have you tried, AJ? Try. What's going to happen to the ammonia's concentration here? If you add ammonia, what's going to happen to the concentration of ammonia?
It's going to suddenly increase.
It's going to suddenly increase.
And then gradually decrease.
Okay. Oh, sorry. I should have made these graphs longer a little bit, like that, just to show that there was a period in time where the equilibrium was set. So at time T2, or we can say T1. At time T1, you have added ammonia. So there. At time T1, you add ammonia. Depending on how much ammonia you add, the graph is going to shoot up. Okay? Now you've got more ammonia. What is going to happen to the hydrogen's concentration?
It's going to favor the forward reaction.
Yes, you're right. You're speaking the right language. So it's favoring the forward reaction, meaning
more.
it's making more nitrogen and hydrogen.
Yes, gradually
Okay.
increase.
So it's going to gradually increase.
Yes.
Okay. So this is going to gradually increase, and that one is also going to gradually increase. And they'll increase like they're in tandem. Do you understand what I'm saying? Yeah. The distance between the two lines will stay the same, but I can't say they're parallel.
Yes.
So because they will increase in tandem, they will increase by the same amount. They're not equal, but they increase by the same amount. And what's going to happen to the forward reaction as it takes place? It will decrease.
Until it's below the H2. Yes.
So this is the concentration of the ammonia and how it will change to re-establish the equilibrium. That is the concentration of the hydrogen and how it will change when ammonia was added to the system. And this one is the concentration of the nitrogen and how it will change after ammonia has been added. Now, grow please and do it for the removing of ammonia. Talk to yourself while you're drawing it. Draw it from the start.
Can I make another line and mirror T2? And do it?
Yes, you can. So removing ammonia is going to slow down all reactions. Okay, you are favoring the reverse reaction. So let's go. Can I go now from the point where we have T1? So this is now T1. That is the point where, no, let's go to T0. That's the point where we have ammonia in equilibrium with hydrogen and nitrogen. No, I'm starting from, because the graph, I'm starting from here. I'm starting here. Where equilibrium is. You can copy that if you want to. You can copy that, but I want to, this is at equilibrium. So this is from T0 to, that point is T1. At T1, what do we do? We drastically drop the ammonia concentration. Now, up to where you want to drop it, I don't care. You drop the ammonia concentration. If you want to drop it down, long down, it's fine. Doesn't matter. Okay? So you drop the concentration of ammonia. Okay, let's go down. There. Gone down. Now you're favoring the reverse reaction. What's going to happen to the concentration of nitrogen? It will definitely decrease. What's going to happen to the concentration of hydrogen? It also decreases because you're favoring the reverse reaction, and the reverse reaction uses up hydrogen and nitrogen. Okay? What's going to happen to the ammonia now? It will increase. Until new equilibrium is reached, and our new equilibrium is reached there where the graph starts going flat. So that is T2. Your graphs went up again. I don't understand why. So this is the concentration of ammonia graph. The green one is the concentration of hydrogen graph, and the black one is the concentration of nitrogen graph. Okay. Just to clarify which reaction is favored. By adding ammonia, you favor the forward reaction. You favor the reaction that makes nitrogen and hydrogen, because that will use the ammonia up, or try to use the ammonia up. So if you look at the graph, the increase in concentration of nitrogen and the increase in concentration of hydrogen means that that reaction making hydrogen and nitrogen is favored. If we look at removing ammonia, we remove the ammonia, so it favors the reaction that makes more ammonia. And how do you see it makes more ammonia? The concentration of the ammonia increases gradually, while the concentration of the hydrogen decreases, the concentration of the nitrogen decreases.
So if the equation was the other way around, then adding NH3 will favor the reverse reaction.
Yes.